All right, welcome to the next video. We are going to talk about average atomic mass today. So we just got done talking about atomic structure, and what that means is talking about what makes up atoms, right? The subatomic particles. We also learned about isotopes, right? Isotopes are different versions of the same element that differ in terms of the number of neutrons, right? And ultimately, that leads to a difference in atomic mass. So what we're going to do today is we're going to learn how to take all the different isotopes of an element and combine them together into an average mass. Okay, so we're going to learn the process by which you do that, along with some other things. But first, though, I want to talk about a little thought experiment that I have for you. Okay, so imagine that you're in a room with 30 kids. All right, kind of hard to imagine given our current coronavirus situation. But imagine you're in a room with 30 kids. 29 students are 5 feet tall, right? So 29 of them are all the same height, 5 feet tall. The final student is 6 feet tall. Okay, so it's like one tall person in a sea of relatively shorter people. The question is, what is the average height of these students? So take a moment to think about that. I'll sort of walk through what my thought process is, right? An initial answer some of you might be thinking is 5.5. Well, that would be sort of the in-between of those two heights, but the problem is that's not really what an average is, right? The average takes into account like all of the students, right? And 29 of them are 5 feet tall. Only one student is 6 feet tall. So it's definitely going to be, it's not going to be 5.5. It's going to be closer to 5 feet. But it's not going to be exactly 5 feet, right? Because we do have this one person who is 6 feet tall. So the exact answer is probably somewhere just a little bit taller than 5 feet, right? Maybe 5 feet and half an inch or like a quarter of an inch, something like that. What we're going to be doing today is learning how to do calculations like this, okay? Because it's the same sort of scenario as calculating average atomic mass. And you'll see that here in just a few minutes. So let's do a little bit of review from what we looked at last time. We looked at the isotopes of hydrogen, right? And the three different isotopes of hydrogen are hydrogen 1, hydrogen 2, hydrogen 3. And they differ due to their number of neutrons, right? Hydrogen 1 only has one proton here. So, and remember, the electrons sort of have a negligible mass. So in terms of the mass of the atom, we really only care about this one proton. That's why this is called hydrogen 1. This is called hydrogen 2 because we have one proton and then one neutron, right? So we've added a neutron here. And then we've added one more neutron to get to our final situation, which is called hydrogen 3. And you may recall that I talked a little bit about the relative, not popularity, but like which one of these is more common, right? And I mentioned that hydrogen 1 was way more common than the others. Let's also look at the periodic table. This bottom number here is called the atomic mass, right? Let's not use that word weight. Let's call this the atomic mass. And it's not a whole number, which is strange, right? Because the masses of these different atoms here are whole numbers, right? This is 1, 2, and 3. But our atomic mass on the periodic table is not a whole number. It's just slightly north of 1, right? Well, this is kind of the same situation that we were looking at here in the thought experiment, right? What this tells me is that the average mass, that's what this is, the average atomic mass. The average mass of hydrogen is very, very close to 1. That means that this isotope right here is way more common than these heavier versions. But there are some of this that do exist. So this answer here, this is what we're going to learn how to calculate, okay? And you need two pieces of information. We're going to get into it in just a minute. But you need the mass of the different isotopes, and you need a percentage of like how common each one is compared to the other. Okay. Before we get into the calculation, though, I just want to spend a moment talking about how we collect this data. So the average atomic mass of an element is the weighted average mass of all its naturally occurring isotopes. All common elements have more than one naturally occurring isotope, okay? So how do we get these percentages, right? How do we know which one is more common than the other? You can do this using a device called a mass spectrometer, okay, and that's what this diagram is. I don't need you guys to know the details of how a mass spectrometer works. We talked about this in AP Chemistry this year during like our third day in AP. We were talking about mass spectrometers. What this device will do is it will take a sample of an element, split it up into its different isotopes using a magnetic field, and then this detector will tell you the relative abundances of each isotope. That's a term that you're going to want to write down and remember. Relative abundances. These are the percentages of each isotope, right? So an isotope that's more common is going to have a higher relative abundance than another isotope would. This is the type of data that you get from a machine like that. You get big peaks wherever you have lots of an isotope. So for this element, whichever element it was, mass number 20 had a very high peak. That means that the isotope 20 version of whatever element this is, it turns out to be neon, okay? That means that neon 20 is the most common isotope of neon. Neon 22 is the second most common, and neon 21 is the least common. We're not going to be working with any sort of graphs like this. Once again, this is something that you would see in AP, but I just wanted to introduce it to you so that you knew that it was there and that we actually do collect this type of data in real life. Okay, so we're going to use what's called a weighted average formula to calculate average atomic masses. A more common application of this formula, however, is useful to you directly as a high school student. Okay, so the first time we actually look at this formula, we're not going to look at it in terms of an average atomic mass. We're going to use this formula to calculate GPA. Not necessarily your GPA, but we're going to use it to calculate a student's GPA. You can use it for that purpose. Okay, so let's consider the following scenario here. Sally has 8 courses, and these are her grades. She has 4 A's, 3 B's, and a D. What's her GPA, right? We can kind of guesstimate it, right? You guys know that A's are like a 4 or a 4.0, right? B's is like a 3.0, and a D is a 1.0. Like if you had all A's, you'd have a 4.0, all B's would be a 3.0, all D's would be a 1.0. So those are sort of the values for those different grades. Sally has like basically half A's, half B's, so maybe she's around a 3.5, maybe a little bit higher, but then she has the one bad grade, right? The 1D. So this is going to bring her average down just a bit. So the question is, like, how much does it bring it down, right? What is her overall GPA? We know it's going to be about 3.5, maybe 3.6, 3.65, something like that, but then it's going to get brought down quite a bit due to this D. So let's see if we can figure that out. I'm going to transition over to my document camera over here, and I'm going to show you how to calculate this. So Sally has 4 A's. I'm going to make a little table here that has the value, okay, so like how much an A is worth, and then the abundance, okay, for each grade. I'll talk a bit more about this as I keep going here. So let me make the full table here. Okay, so A's, B's, C's, D's, and F's. Okay, so Sally had, let's do the abundance first, okay? So she had 8 classes. So the abundance of A's would be 4 out of 8, okay, which is 0.5. Another way to think of this is 50%, right? So Sally, her abundance of A's was like 50% of her grades, right? 4 out of 8. And A's are worth a 4 or a 4.0, right, on the GPA scale. Let's fill that in. B's are 3.0, C's are 2.0, D's are 1.0, and F's are worth nothing, right? If you have an F, it does not contribute to your GPA at all. Well, it does, but it brings it down because you don't get any credit. Okay, Sally had 3 B's, so 3 out of 8. This is equal to, let's see, let me get my calculator pulled up on my phone here. Okay, you guys can see that, 3 out of 8. Okay, this is 0.375, or 37.5%. And then she had 0 C's, so 0 out of 8 is just 0. And then 1D, so 1 out of 8 for the D. Once again, 0.125, or 12.5%. Okay, I want to say something real quick. Oh yeah, and then 0 Fs, right? Oop, 0 out of 8. I want to make a note here real quick about these abundance numbers. This decimal version is actually the number that we're going to use in the formula. When you're talking about percentages or about abundances, however, you can reference the percentages, but we're always going to use the decimal version of the percentage whenever we use this formula. Okay? So let me scoop my paper up a little bit here and let me show you how the formula works. Okay? So her GPA, or her grade point average, is equal to the value of the first type of grade times its abundance. So 4.0 times 0.5. Okay? And this right here is for A's. And all you have to do is add this together for each type of grade. Okay? For each grade. So for B's, we have 3.0 times 3 over 8, or times 0.375. You can actually put it in as the fraction if you want to, but the decimal will also work, right? Because these are technically equal to each other. And we're going to add that to, okay, the only other one we have to worry about is the D's, right? Because this value here is 0, right? And if you multiply something by 0, the whole thing goes to 0. So like the C's and the F's, we don't actually have to worry about that. So the only other part that we have to worry about is the D's, and that's going to be 1.0 times 0.125. Okay, so this once again is for the B's, and then this is for the D's. Let me scoop this up a little bit more. Okay, let's find out what our final answer is. I'll open up my calculator one more time. Okay, pretty easy to just type this all in. So it's 4 times 0.5 plus 3 times 0.375 plus 1 times 0.125. Okay, your calculator is pretty smart, so as long as you type it in just like that, you actually don't need the parentheses. Multiplication takes place before addition in the order of operations. So as long as you type it in just like that, you don't even need the parentheses. But if you want to use the parentheses just to be safe, that's probably a decent idea. Okay, so there you go, 3.25. That's her GPA. Okay, and so like we saw here, we were expecting it to be about 3.5, but drawn down a bit due to that D. So she does lose maybe 0.3, 0.4 points off of her GPA from having that 1D. So that's how important it is to have your overall grades be good, right? You don't just want to pay attention to one or two particular classes. You want to make sure that you're doing a good job in each class to keep your grade point average high. Okay, so the generic formula for when we do this with average atomic mass instead of grade point average is basically the same thing, okay? We're still going to have that abundance in there. The difference is, instead of using the values like 4, 3, 2, and 1, right, for an A, B, C, or D, we're going to use the different masses of different isotopes. Okay? But all you do is the same thing, right? It's mass of one isotope times the abundance of that isotope plus mass times abundance plus mass times abundance for however many isotopes you have. Okay? And here's a reminder again one more time about these abundances, right? These have to be in decimal form, right? So 50% would be 0.5, 5% would be 0.05. Make sure that you are using the decimal versions of percentages, or else your answers are not going to come close to making any sort of sense. Okay? So let's do an example. There is a really, really great website that contains information about isotopes. It's called ptable.com. It stands for like periodictable.com. Let's use this website to calculate the average atomic mass of chlorine. Okay? I'm going to pull this up. When you go to this website, click on the Isotopes tab. Okay, so there's 4 tabs up here at the top. Click on Isotopes. Okay? And then for any element, all you have to do is just click on the element. And you see how it's expanded out with all these things off here? I'm going to drag my bar over here so we can see all this. These are all of the different potential isotopes of chlorine. That's a lot of information, okay? We are only concerned with naturally occurring isotopes, okay? What that means is that we are interested in this type, the stable type. All these other types decay over time, meaning you don't really find them in nature, okay? They have to be made artificially in a lab, or they can be made in nature, but they soon after decay into a more stable version, okay? So we're concerned with the stable versions of the isotope, the black border. You see how when I hover over these different types, I ordered some food, it's here, I'll get it in a few minutes. You see how when I hover over these different types of borders here, it like highlights them over here. So if you hover over the stable isotopes, you can see that there's only two. Chlorine 35, you see that top number there, and chlorine 37, okay? Those are our two isotopes. And if you click on it, it'll actually bring up some information from Wikipedia. And you can see here off to the side, it's got some information about the isotopes of chlorine, specifically the abundance, right? And that's what we need. All right. So let me go ahead and write this down real quick on a piece of paper, and I'll show you how to use this data to calculate the average atomic mass. So 76% for the first one, and then the remainder, 24%, for the next one. So let's go back to my document camera here. Okay, so the two isotopes were chlorine 35 and chlorine 37, and they had these abundances, right? So this one is clearly more common than this one is. So how do we calculate the average atomic mass? I'm going to abbreviate that AAM, average atomic mass, and it's the same type of formula, right? My value is my mass, okay, so 35, and then I'm going to multiply that times my abundance, but I have to use the decimal version of the percentage, so 0.76. And then I'm going to add that to the mass of the second one times the percentage for the second one, 0.24. Okay? So, very, very simple. Let me pop up my calculator here. Okay, so we've got 35 times 0.76 plus 37 times 0.24, 35.48. So that's the value that we get according to the data from this website. Let's go look, right, 35.48. Let's go look at the periodic table, okay, the one that I've given you, and let's see how close that matches up to the value on the periodic table for chlorine. There's that value right there, 35.4527. Pretty close, not exact. The reason that it is not exactly the same as the value there, there's a couple of factors at play. First of all, there are trace amounts of another isotope. Trace means that the percentage is very, very small, but it is there. So that can impact things just a little bit. Another reason is that these mass numbers here, 35 and 37, sometimes scientists use a slightly different number that isn't a whole number for the masses. That's not something that we need to worry about in our class. So the value that we got, 35.48, that is close enough to this value here for us to be satisfied. Okay, and remember the objective for today, right, is just to be able to do these calculations in the first place, not to necessarily get the exact number on the periodic table, but it should be close. Okay. All right, last slide for you guys. There are a few things that I need you to make sure you're paying attention to as you work on these types of problems. Number one, abundances for isotopes of an element should always add up to 100%. Okay. Or if you're using those decimal versions of the percentages, those should add up to the number 1, right? So please make sure that your abundances always add up to 100. If they don't, then you are not going to get the right answer, okay? Second rule, the average atomic mass for an element must be in the range of the individual isotope masses. So think about that, right? We just looked at an example. I'll show you one more time here. We were looking at two different versions of chlorine, right? Chlorine 35, chlorine 37. What that statement means is that the average atomic mass for chlorine must be in between 35 and 37. The average can't be less than 35 or greater than 37. It's got to be in the range of those isotope masses, right? And that makes sense, right? If you think back to our height example from the very beginning, the shortest person was 5 feet tall, the tallest person was 6 feet tall. It would make no sense if you said that the average was 4.5 or 7 feet, right? The average has to be in the range of the smallest to tallest person, or the lightest to heaviest isotope, in order for things to make sense. Okay, that's it for today. We're going to be doing some calculations on average atomic mass, and I'll talk with you a little bit more about that in class next time. Thanks.